Suppose, like yesterday, we said that metric path planning, that means we need some calculations. We need to calculate or measure the distances between the nodes or actual objects. So path planning techniques are divided in two parts, qualitative and metric. Then qualitative techniques we learned about relational or graph search methods, then associative methods. Now we want to discuss with metric path planning. Here we have two types of algorithms are there. One is a start search and other are wavefront propagation methods. Out of this A star search we have discussed, still we will see how it is applied. Already we have worked with A star, how A star calculates the path or how it search exactly the route using the calculation and formula. Still once more we will apply this to the actual conditions. Now metric path planning, how it is differ with topological path planning methods. So metric path planning methods are actually measurement based methods. They have some sensors or some data. They can measure the coordinates or the object positions. They can decompose their coordinates in XY mode or in 3D mode. They can produce exact route with given landmarks or gateways. But in topological parts, we produce route using landmarks and gateways. In metric path planning, we base ourselves onto measurements or we find or decompose the path using waypoints or coordinates. Now, metric path planners are most probably exact or they are going towards exact. Metric path planners are having configuration of the space. Many times they can use grids to decompose the space. So whatever view they are getting or whatever the measurements they are getting, they can produce that measurements on grids. So graph like view we can see or map like view we can see, and we can decompose the path and subpaths or goals and sub goals. Now there are two types of algorithms. One is graph search problems. So they use coordinates. They treat view on grids, that is coordinate system, and then search the position or goal. They decompose the total path in different small sub goals, and then overall goal can be achieved. Here also we can decompose the nodes to find out sub goals. In second method, they are graphics coloring methods. These are some advanced methods where using arrow projection or color projection or using flow projection, we can find path to the actual destination or goal. Now, first of all, why all these things are required? Because see that robot is viewing all the world or whatever 3D world, and that is mentioned in the mission path planner or mission planner, where pathfinding is one of the section. So some spatial memory is allocated, and here in mission planner one of the major tasks is path planning. So where is the current position and what is next position, that is what exactly we are giving path planning. Now here this program unit, hardware and software, major tasks are first of all acting like watchdog are acting like attention unit. Similarly, defining obstacles, that is what reasoning we say, avoiding obstacles, finding optimal path, collecting more and more information so that paths can be simplified. As we see, there are two forms, that is route, that is qualitative path, or layout is a metric path. Layout is generally grid, route is connectivity between the nodes. Layout is there, that is once we find layout based on metric measurements, we can place route in that. Once we have measurements, we can use topological terms in that layout or metric path. But whenever I use on gross level topological path planning, I cannot use metric part over there, because in topological path planning, overall method or projection is different than metric path planning. Now, how to represent this path planning? So there are many methods, or many times we have to develop our own algorithms depending on the task, depending on the layout, depending on the area, and designer has to select either quantitative or metric maps. Now many of you wondering, if there is a metric map available, then why you are going to quantitative path? This is obvious question. Or if metric maps are ideal or they are giving you correct positions, then why you need topological path planning? Reason is very simple. Sometimes areas are very large. The metric measurements are not so accurate. Many times GPS accuracy is also problem. Many times sensor limitations are there, range problems are there. So every now and then for a large area, I cannot establish metric maps correctly. So I have to rely on topological path planning, or I can go to the hybrid way. Now metric maps, they use measurements for planning. They are interested for best or optimal path, not like topological path planning. Topological path planning refers for available path that might not be best. On the contrary, metric map always goes for best or optimal path. Many times, path planning units assume that some prior map also or some references are also there that can be used if already map is available, or the projections are available, or the some metric kind of things are available that can be used in metric maps. But in topological path planning, every now and then we have to scan and find the best. Another very important property about metric maps, they use configuration space, that is what Cspace. This depends on the view what robot is looking at objects, that is 6DOF view. Many times some systems if do not have 6DOF view, then they can decompose in 3DOF view, where whatever space you are looking, that is what Cspace we say now, that will be simplified, that will be taking measurements and considered for the path positions. Here exact location and orientation will be found out by that coordinates or measurements what we have done. Now in metric path planning, how to decompose this configuration space? Once again I repeat, what is configuration space? Suppose your robot is moving in 3D world. It has got camera or sensors. Now we want to find out path. So robot is at starting position. So here robot is having 3D world around it. And it has to start in that overall space. That is what configuration space. And in that configuration space, it has to find its location, orientation, and next location and next orientation. Current location, current orientation, and then next location and next orientation. Once it goes to next, current will be becoming previous, and again you have to find next. So you need to decompose this space. That is what you want to find. So this space, that is what real life, real world space, how you will be projecting and using for measurements, or how they can be decomposed using radar, camera, like sensors. And you need to apply execution algorithms on them. Now decomposition of this sea space is based on Meadow Maps or Generalized Voronoi Graphs, or sometimes regular grids or chord trees. So these are space decomposition techniques. How you can decompose the space.